This is Kevin Cole at the University of Nebraska. The topic is thermodynamics, and the example is entropy production. The device we're looking at is an open feedwater heater. We're given some inlet states and some mass flows. We're given a water coming in at 45 C at 4 kilograms per second. We're given steam coming in at 250 C and 0.5 kilograms per second, and we're given an outlet state we don't know. We're going to discover that, and all of the states are at pressure 600 kPa. It needs to be equal pressure so they can get the two flows in. We're told to look for the exit temperature and the entropy production rate, and we're told there's no external heat loss. Relationships we're going to use are conservation of mass. The inlet flows have to add up to the outlet flow. That's for steady conditions. And for energy conservation, this is the same as for a heat exchanger. And that is that the enthalpy is the important quantity, and the sum of all the inlet mass flows times each of the inlet enthalpies is equal to the sum of the exit mass flows times each of the exit enthalpies. So the place to start is with the mass conservation. We know also, because we have three states, I made a table down here, state 1, 2, 3, and I put in the mass flows that we know, the temperatures that we know. We're going to look for, we're going to need enthalpies and entropies to solve the problem, so I've left space for those, and they're all at the same pressure of 600 kPa, so that's what we know to start with. Let's start with mass conservation. We can just add up the two mass flows we know. 4 plus 0.5 is going to be equal to m dot 3, which is 4.5. So I can put in here 4.5, and these are in kilograms per second. That takes care of mass conservation. Now I want to also, before I do the energy conservation, I want to fill in the stuff that we know. I want to fill in H and S for the states that we know. So let's start with state 1. It's a subcooled liquid. At 45 C, at pressures above atmospheric, water is liquid. We're going to use the approximation that the enthalpy we're looking for at a particular temperature and pressure is approximately equal to H at the saturated liquid condition at the correct temperature. This is a good approximation for compressed liquid. We're going to do this for state 1. Let's go find a compressed liquid table, and find a saturated table and straighten this out. So state 1 is, here's a saturated water table on temperature. Here's temperature in C. 45 degrees is here. We're looking for the saturated liquid value of the enthalpy and the saturated liquid value of the entropy. So coming across here, the enthalpy value we want is 188.45, and the entropy value we need is 0.6387. Let's transfer those values back to my little table here. So we've got, for state 1, 188.45, and for the entropy we've got I'm going to round this off, 639. All right, state 2 is, I'll jot it down up here. State 2 is superheat. We're told that it's steam. It's 250 C and 600 kPa, so it's a superheat table. Let's go find a superheat table and find those values that we need. We're going to need a superheat at 600 kPa. Let's go find that. Here's a superheated water, and these are in blocks, and the 600 kPa block is listed here as 0.6 megapascals. It's the same as 600 kPa, and the temperature we need is 250 C. Here's the temperature column in C. So there's 250. We want to come across and look for H and S. So where these columns coincide, there's the H value of 2957.6, and there's the S value of 7.1833. Let's transfer those back to my little table here. So the state 2 is the superheat. The H is 2957.6, and the S is 7.18, I'm going to round it off, 183. All right, now we're ready to use the energy conservation to look for state 3. We're looking for the temperature. We can use this equation to find S. Let's write this out. For the inlet states, we've got two of them. We've got m dot 1 H1 plus m dot 2 H2. And that's equal to the sum of the exit states. There's only one of those, m dot 3 times H3. And then I know everything except H3, so let's solve for that. H3 is going to be 1 over m dot 3 times m dot 1 H1 plus m dot 2 H2. And let's put some numbers in. H3 is going to be 1 over 4.5 kilograms per second. Then m dot 1 is 4. H1 is 188.45. M dot 2 is 0.5 times H2, which is 2957.6. And the units on mass flow drop out. We get back the units of H. So when I crunch H3, I get 496.13 kilojoules per kilogram. In fact, I could write that in here, 496.13. So that's H. I can find the temperature if I can go to an appropriate table. What phases are present? What phase or phases are present? If you don't know what phases are present, always start with the saturated table. And what do we know? The saturated table, we could look in a pressure table at 600 kPa. So let's do that. And then it'll tell us what's going on, and we'll be able to figure out the state. So let's go find the saturated table on pressure. Saturated water pressure table. We're coming in at 600 kPa, as pressure in kPa is 600 right here. And we've got a value of enthalpy we're trying to figure out where we are. Well, here's enthalpy. And in the saturated condition at 600 kPa, enthalpy lies between 670 for the saturated liquid and 2756 for the saturated vapor. Our value is below this 673, so that says that the phase present is subcooled liquid. Now, to get the subcooled liquid situation, we're going to use what we used before. We're going to say that the H is equal to the saturated liquid value. This is approximate at the correct temperature. So we could look for our 496 value in this column right here. And it would fall, 496 would fall in between here, and the temperatures would fall in between here, but I'm going to be lazy. So we could interpolate right here and be done. But I'm going to go find a saturated temperature table. Let's see, I think I've got one. Yeah, here it is. Here's a saturated temperature table. I'm going to look in the saturated liquid value of the H for 496.13. 496 falls in here. So then the temperatures are between 115 and 120. I'm going to interpolate here. So you can check my interpolation. I'm going to say at this value of H3, find T3 equals, I found 118 C, and this was from the saturated temperature table. And again, you could have also used the pressure table with a little more difficult interpolation. Oh, while I was there, I should have also found S at T3 for a saturated liquid or subcooled. You can use the same approximation. Notice to say S at TP is approximately equal to S saturated liquid. And we could look that up. Let's go quick look at that. Nope, it's this one. That would be interpolating on this column. The saturated liquid value of the entropy would fall in between here and the value that I got there. I would just transfer it back. It was 1.503. Let's put that here, 1.503, 1.503. We're going to need that for part B. But here is the response to part A. The temperature is 118 C. And so we've warmed up the water quite a bit. It started from 45 and it came up to 118 C. So this thing is indeed a feedwater heater. That's pretty warm. Part B, what is the entropy production? The entropy balance for an open system with flow, if it's steady, we've got this left-hand side is 0. There's no storage term. Entropy balance says 0 equals the sum of all the heat flows divided by each of their temperatures plus the sum of all the inlet mass flow rates times each of their entropies minus the sum of all the exit mass flows times each of their entropies plus sigma dot. And this sigma dot, that's the entropy production rate, or sometimes just called the entropy production. Let's solve for that. I'm going to kill the Q term because we're told there's no heat loss. No heat loss to the control volume that's around the whole body. Let me scroll down a little bit. There's no heat loss to this control volume, or this system here. And that's what this refers to. So we drop that term and solve for these other guys. I'm going to have the sum of the exit m dots times the exit entropies minus the sum of the inlet m dots times the inlet entropies. And we could write that out in terms of, there's a single exit term, that's going to be m dot 3 s3, and there's two inlet terms. One of them is m dot 1 s1, and the other one is m dot 2 s2. So those are both subtracted. All right, I've got all these quantities. I can turn the crank now. So my sigma dot is going to be pulling values from the table. M dot 3 is 4.5. S3 is 1.503. I've got 4 for m dot 1 times S1 is 0.639, and I've got m dot 2 is 0.5, and S1 is 7.183. And when I turn the crank on all of that, I've got 0.639, and the units are kilograms per second times kilojoules per kilogram per Kelvin. So kilograms go out, and a kilojoule per second is a kilowatt. So I've got kilowatts per Kelvin. So that's my entropy production rate. So my conclusion here is that sigma dot is positive. That is to say, the entropy increases. And that's a statement that come on, scroll for me, please. That's a statement that the mixing, because this is a kind of a heat exchanger where there's mixing is non-reversible. And the increase of entropy principle says that for an adiabatic system, sigma dot is greater than or equal to 0, and it's greater than or equals for a real situation. It's equal to 0 for its ideal only. And this is a real situation because it's non-reversible. And this thing is the increase of entropy principle. We can only talk about that for adiabatic. All right, let's recap. We're looking at a feedwater heater. We're asked to find the exit temperature and the entropy production rate. We had to find some states. If the state was subcooled, we're going to use the approximation that we can find the enthalpy and the entropy by looking at the saturated liquid condition at the correct temperature, and we're ignoring the pressure. We also use a superheat table to find state 2. We conserved energy by using a heat exchanger relationship and found the final H, but we didn't know the phase, when you don't know the phase, start with a saturated table. Then if the value comes out below, it's subcooled. That's what we found. If it turns out beyond the table values, then it's superheat. So if you aren't sure, start with a saturated table. And then when we did an entropy balance, we had simplified it because there was no heat loss, and looked for the entropy production rate. We needed all the entropies, and we found that the entropy production rate was positive. So entropy was increasing, and that's an indication of a non-reversible process. And if you remember that in an adiabatic system entropy increases for real systems, then all will be well.